The term functor comes from category theory, in which a functor is a data type that preserves the structure of a piece of data as it's mapped from one category to another. Although the name may sound foreign, we work with functors all the time in JavaScript, given that the array data type is technically a functor. As you can see, it provides us with a container to wrap our value, and it also provides us with a map interface. The map interface is arguably the most important part of a functor, as it allows us to transform our value from one type to another without causing any harm to our data. There are many common functors and monads that you find working in functional programming. Now we're going to implement the identity functor, which is the most basic of them all. Now this is going to take a value x and return an object. Now, inside our body, we can add different methods that will allow us to act on the data with which our functor is holding. Now, as we just learned, map is crucial, so this will be the first method that we'll add. This map is going to take a function, which will then be applied to the value being held inside of our container. From this, we're going to return a new container because we want to be able to preserve that context. This way, we know we'll be able to continue safely transforming our values until it's time to pull it out and use it. And that leads us to our next method, value of. As you can see, value of is just going to be called with no arguments, and it's just going to allow us to unbox our data that's being held by our identity functor. Now, we can call our identity function and pass in the value of 10 into our box, and we'll see that we have these map and value of methods on there. Now, if we add an inspect method, we'll see that this is automatically going to be logging for us. And we'll set it up just so it prints identity and then the value. And we see identity 10. Alright, so we have this identity functor, but we need to be able to make sure that it abides by the functor laws, or else we won't be able to compose it with other functors and leverage all the true power that algebraic data types give to us. Now, the two functor laws are identity and composition. If you're familiar with functional composition, then you might be familiar with these. First, I'm going to create a variable and set it equal to the identity function with some number, 1992. And then below, I'm just going to add the identity function, which we'll use to test. Alright, now that we have our test property set up, I'm going to create two variables, a and b. And a is just going to be equal to that x that we just created. Following this, we're just going to set b to the value of a.map with the identity function. Alright, now that we have that set up, I'm just going to call that compare function I've imported above. And I'm going to pass in a.mapid to the first argument, and then b.mapid. And as we see if we evaluate them, that we're both getting true. Now, one thing to point out is that this compare function is calling toString on both of these values under the hood. This is because of how JavaScript treats non-primitive values like objects. Specifically, they won't allow us to test for equivalence, thus forcing us to transform our values to a primitive value like a string before comparing. Carrying on though, the next law we need to test is the composition law. Alright, so to test composition, we need to map over our identity functor, and we're just going to pass in the square numbers function, which is going to square 2000, and then we're going to map again and pass in times 10, which is going to multiply the result of square numbers times 2000 times 10. Alright, now, to prove this equal, we're only going to use one map, and we're going to use map's callback function to transform our value in one fell swoop. Alright, now instead of chaining maps, we're just passing in square numbers to our times 10 function, and then the most nested part of this is our x value, And we should note that these functions are going to fire off from inner outer. And as a result of that, comparing the function up top, where square numbers is applied first and then times 10 is applied second, will give us the same value as we just produced here on the second line. And that just about wraps up this video on functors. Just to recap, in order for a data type to be a functor, it must implement a map method, and it also must abide by the identity and composition laws that we just tested out. Below identity, I'm going to create another functor called maybe. Now, whereas identity always applied the function being input to its map function to the value that it contained, the maybe functor is going to be a little bit more cautious before applying this function to just any value. Specifically, maybe is going to avoid null and undefined at all costs. To do this, we'll define a helper function is nothing, which is going to take in some value x, and it's going to check if x is equal to either undefined or null. If it ends up being either of these values, then is nothing is going to return true. Otherwise, it'll return false. If we test this out, we see that null prints out true. We pass in a string value here. It's going to print out false. All right, now that we've tested our is nothing function, let's go back into the body of our maybe function and uncomment out that map. Now, as we know, map will take a function as its input. Before we go ahead and apply the input function to the value of our functor, though, we're going to want to call is nothing and check whether the value wrapped inside of our maybe is null or undefined. If it is, then we're going to halt our program and just return a maybe of null. Otherwise, we're going to apply the value of our maybe to the function being input to map and return its result wrapped inside yet another maybe, thus preserving the structure of our data. Let's just wrap this up by adding the value of method. That would just allow us to retrieve our value from its container. And then also let's add the inspect method, which will just allow us to quickly take a peek at the value our functor's holding. All right, now that our function's ready to go, we can create our maybe functor by just instantiating this maybe function. And here, I'm just giving it a value of 10. And if I run the map method and pass in times 10, we'll see that logging out this value returns 100 because 10 times 10 is 100. So that's working out well for us. All right, now to wrap this up, let's make sure that our maybe functor abides by the functor laws so we can sleep well at night knowing that our data type is in fact a functor and not just an imposter. Additionally, by checking the functor laws, we can ensure that if we ever want to use this type of data with another functor data type, then we could do so without any issue. And that's really powerful, especially when you start digging into other types of functors like monoids and applicatives. Let's not worry about that just yet though. For now, let's focus on proving the identity and composition laws for our maybe functor. Okay, first we're going to test out the identity law. So the identity law states that if a functor x is given the identity function, then it should return a functor of x. So basically whatever's input needs to be output. Therefore we could just simulate it like so. Now this should be equal to the value of maybe wrapped around the number 10. To perform this comparison, we'll use the value of method of our maybe. And this is going to pop out our value, which is 10, and then compare them. And as we see, running this code gives us the value of true. All right, now that our identity law check is finished up, we can test out the composition law. And so inside this log statement, I'm just going to say maybe of 10 again, and then I'm going to chain two maps. And again, I'm going to use value of to pop off the value of this computation. Next, we'll set up our comparison. Again, I'm going to use triple equals. And instead of chaining two maps, I'm simply going to invoke our map and pass its value first into the times 10 function. And then immediately following this, I'm going to wrap this with the square numbers function. And now, if we run this code, we see that true is printed to our console twice, meaning that both our identity and composition law checks have passed. Semigroups provide us with an interface for combining one or more values together. So here, I'm just creating a semigroup called sum. And so the first thing we'll do is just set the value being passed in. Now the next thing we'll need to do is add a concat function. So all semigroups need to have this concat function. And so what this is going to do is it's going to take in another semigroup, and in this instance it's going to use addition to combine both of these values. And keep in mind that we're wrapping this return value in a sum, as this will allow us to continue concatenating values for as long as we need. So now I'm just going to add a console log statement, and if we have a sum of 10 and we concatenate that with a sum of 20, we should see that we get 30 as our result. Now if I just execute this code, remove these statements, and okay. Now if I execute it, I see that we get that value of 30 inside of our object. So below our sum semigroup, I'm going to create a product semigroup, and we can pretty much just copy the details and paste them below. However, we'll need to return a product from our concat, and we'll also need to change our addition to perform multiplication. Okay, so rather than logging this out, I'm going to create a unit test, and we'll say our product semigroup async assert. And then we're going to say a product of 10, and we're going to say given concat product of 5, concat product of 2. Should return a value of 100. So here, I'm going to say result equals product of 10, concat product of 5, concat product of 2. And we're going to say result, and the expected is going to be 100. Oh, and see, we need to peel off the value. We can actually use our rammed function. So we'll say equals result.value, and then 100. And then we'll just write true here. And now we see that our test is passing. So below this, we're going to test the associative nature of semigroups. In order for us to be working with a semigroup, it must be associative. And that simply means that we can perform these concatenations any way that we'd like. So here we'll just do const first equals, and then we're going to set it equal to this one right here. And then our second, so instead of having it just like this, the value of 10 times 5, we're going to concat directly onto the product of 5. So we'll do equals first dot value and second dot value. And rather, so we'll see, regardless where the concatenation takes place. Just to see this run, boom, we see that our new test case is passing. And although it might seem like a minor detail, it's extremely important that our semigroup possesses this attribute of being associative, or else we won't be able to harness the true power of semigroups. So below our product semigroup, I'm going to create another semigroup called max. And this is going to compare two values and give us the greater value. So first, we'll just be setting the value. And then the second thing we'll do here is add our concat function, as every semigroup must have. But instead of multiplying our values, we're going to use math.max. And then it's going to give us either the current value or the value that's being passed in, depending on which one's bigger. And I'm just going to copy this and create a min as well. And instead of math.max, we're going to use math.min to get the smaller of the two. So here, we'll just say max test equals max of 10, concat max of 5, concat with a max of 7. And then we'll just have min test. And we'll use the same values, but we'll just use min. And so below these, I'm just going to log out our max test and our min test variables. Alright, and we see that max is giving us the value of 10, and min is giving us the value of 5. So everything's working correctly. You know, and if we change this 7 to a 17, and this min to a 15, we see that this continues to work, as our max test now prints out a value of 17, and our min test gives us a value of 7. On this page, I'm just going to create an any and an all semigroup. And I'm just going to scaffold out this shell for both. Okay, so inside of our any, the first thing we're going to do is set the value, as always. And then below this, we're just going to add a concat function, which is going to use the OR operator to check for truthiness in either the current value as well as the value that it's being concated with. Now below, we're going to do the same for our all semigroup. However, this time we're going to use the logical AND operator, as we're going to need truthiness in both of these values in order for this to return true. Okay, so now that we have those set up, I'm just going to copy our min test and max test variables, paste them down here, and instead I'm going to change their names to all test and any test. And so inside of our all test, we're going to change all of our maxes to all, and we're going to pass in false into our first all, and then false to our second all as well. And the last thing we're going to do is just pass in a true. And then for our any test, copy this line down here and then change our alls to any. And so now if we run these, we need to log them out. So now if we run these, we see that we get a false for our all test and a true for our any test. And as we know, our all test is going to need truthiness in all of our values. Therefore, we'll only get a true if we set all of these to true. So now if we run this again, boom, we see that we're getting true for both. Now if we change our last any to take the value of false, we'll see that this now prints out false, as we have no truthiness in any of these. And if we set all of these values to true, obviously we're going to get a true back. So on our page, we have our product semigroup. So in order to upgrade this to a monoid, we'll need to add an identity function. So to do this, we'll just define a function called empty. And so the identity for product is going to be a product of 1. And this is because multiplying anything by 1 is going to give us that value. All right, I fixed that there. So now to test this out, we'll say const input value equal to 20, and then we'll say const result equals product of our input value. And then so we need this to equal true. And so for our right identity, we'll have result.concat product.empty. And so we're going to say, we're going to pluck that value off, and we're going to test it equal to that input value. Okay, so now if we take a look at this, all right, we see that our test is passing. And so in order for this to be a valid monoid, it will need to possess right and left identity. So now we'll test our left identity, and we're going to flip this around. So we'll have product.empty concat result. All right, cool. We see that our left and right identity are passing. Okay, so to continue, let's do this with another monoid. Okay, so we have our sum semigroup here, but we need to define that identity. And so since we're working with a sum, the identity is going to be a sum of 0, because adding 0 to any value is going to give us that value. I'm just going to copy and paste these tests and adapt them to our sum monoid. And now we see that all of our tests are passing, as we've now upgraded our sum and product semigroups to be valid monoid instances. Although semigroups are powerful, they're not nearly as powerful as the monoid, because they can't handle empty values. But luckily, we can upgrade semigroups to monoids with ease. All we need to do is define an identity function, which is going to come in the form of empty. To kick things off, we're going to define an empty on our any semigroup, and this is just going to be an any of false. Now that we have that done, let's move on to all. So whereas empty only needs one of the values that it's concatenating with to be truthy, all looks for truthiness in all of them. And as a result of that, it has true as its identity. So now that we have these, let's just test them out real quick. And we'll say all that empty concat all true concat all true. And then below this, we'll do the same with any. All right. Now if we run these, boom, we see that we get true for both, which should make sense, granted that we know the laws. And if we decided to just concat the empty on the end, and now we still get the correct behavior. Moving forward, let's upgrade our max and min semigroups. Now, these identities are also going to be very similar. When defining the empty on max, we're going to return a max of negative infinity. And on the other hand, min is going to return a min of infinity, or positive infinity. Now, the fact that max has a negative number as its identity and min has a positive might seem a bit confusing. However, if we just think about it, max is always trying to get the larger of two values. And by having an ID of negative infinity, This ensures that it will always be able to pull out a larger number. Min, on the other hand, has positive infinity because it's always looking for the lower number, and therefore comparing any number to its identity of infinity is always going to return the number being compared. And just to test this out, we're going to add this log statement below. And then again, I'm going to start with our empty and then concat a bunch of mins. And then I'll do the exact same thing with max. And boom, we see that we're getting a min of 5 and a max of 10. And then again, we'll see that everything still works just as planned when we concat these empties onto the end. And now min stays the same, however, max has a larger value now as we've passed in 11. On our page, we have a collection of several different monoids. And at the bottom, we see that we're logging out our product monoid after concatenating it with several different values. And we're doing the same with our sum. And although this will provide us with the values that we need, it's not exactly the most practical way. So let's see another way how we could do this. So here, I'm just going to log out result, which I'll make right here. Above that, I'm just going to create a data variable, and it is going to be just an array 1, 2, 3, 4, 5. And so to use our monoids, we're going to want to map over our data. So if we pass in the sum monoid, we should see that this returns all of these values wrapped inside of that sum monoid. And it does, because we see we have that concat right on it. And it would do the exact same with product. Once you have that, we can then call the reduce method. And we're going to say the accumulator concat with the val. And then so for product, we'll have to pass in product.empty here. And if we take a look at our console, we see that all of our product monoids have been reduced into this single object, which has the value of multiplying 1 times 2 times 3 times 4 times 5. And if we switch this out for sum, we see that we get 15 there. Okay, so now this is more practical than actually manually calling the concat method every time. However, it's still not that general, as we're forced to define the exact monoid that we want to use. And so let's make this a little bit more flexible. So here, we're just going to create a fold function. And it's going to take in a monoid as well as some data, which will default to an empty array. And then it's going to reduce over this data, just like we did up here. We could actually just copy this. Now, instead of sum.empty, we'll change this to monoid. And instead of just concatenating the val like this, we're going to wrap our monoid around the value. And at the end there, we see that the initial value will just be our monoid's empty function. So now, we'll say result equals and say sum and then data. And see, we're getting the exact same value as we were before. And the same will go on with product. And if we wanted to, we could just say const sumFold equals fold, and then pass in sum there, and then sumFold with data. And, to wrap things up, let's say list of bools, and this is going to be a list of Boolean values, and we're going to have all true there. And so we can say fold, and then we're going to pass in our all monoid, and then list of bools. And boom, we see that it's printing out true for us. If we change this to false, we see that it's changing to false. And then we'll do the any type. And, just to check everything out, we'll do the max. And we see that we're getting the max value here in 5. And then if we get min, we see that we're getting 1.